Hello students, myself Dr. Vijay Lakshmi. Welcome to the class Carbohydrates. In the last class, we were discussing about conversion of carbohydrates, interconversion of carbohydrates. So in that, increasing and decreasing the carbon chain we have discussed. Next one is epimers and epimerization. So what are epimers? A pair of diastereomers that differ only in the configuration about single carbon atom are said to be epimers. So when in a compound there are more than one asymmetric carbons are present and that compounds differ in the configuration of only one single asymmetric carbon, then that isomers are called epimers. For example, D-mannose and D-galactose are epimers of D-glucose. See the structure of D-glucose here. D-glucose and D-mannose change only at the configuration of a second carbon. D-glucose and D-mannose change at the configuration of second carbon only. So these two are epimers of each other. See the configuration of glucose and galactose, both changes at the configuration of fourth carbon only. Remaining all is same, only the fourth carbon configuration of D-galactose and D-glucose are changed. Therefore, D-glucose and D-galactose are called as epimers of each other. But D-mannose and D-galactose are not epimers. D-glucose and D-mannose are epimers and glucose and galactose are epimers. So epimers are, these are the diastereomers that differ only in the configuration about a single carbon atom are said to be epimers. So what are diastereomers? In the definition we told that epimers are diastereomers. So diastereomers, these can be defined as those isomers which are not mirror images of each other. So for any compound, how many isomers are possible means the number of chiral carbons, that is 2 raised to n. 2 raised to n. N is number of chiral carbons. So let us see in the example here 4 carbons are there. So 4 carbons means it is butane, and on the second carbon OH group and third carbon Br is present. So it is 3 bromo 2 butanol. For that, in this compound there are 2 chiral carbons. There are 2 chiral carbons. This is first chiral carbon and this is second chiral carbon. So when a compound contains, that is 2 raised to n, the n is number of chiral carbons, 2 raised to 2 is equal to 4. So for this compound 4 isomers are possible. So let us see that 4 isomers. So here structure 1 and structure 2, here 2 isomers are there, structure 3, structure 4. So 4 isomers are written here. Among that, structure 1 and structure 2 are mirror images of each other. Structure 3 and structure 4 are also mirror images of each other. The optical active compounds which are the optically active isomers which are mirror images of each other are called enantiomers. So structure 1 and structure 2 are called enantiomers of each other. Structure 3 and structure 4 are also mirror images, so they are enantiomers of each other. But see the structure 1 and structure 3. These two are isomers, but they are not mirror images of each other. So these structures are called diastereomers. Structure 2 and structure 4, These two are also not mirror images, but they are isomers. So they are called diastereomers. We can take example of 2 and 3 also. Structure 2 and structure 3 both are isomers, but they are not mirror images. So these two are also becomes diastereomers. So these type of the diastereomers which differ in only in the configuration about a single carbon atom are said to be epimers. Epimerization, that is conversion of one epimer into another epimer. The change of configuration of one of the asymmetric carbon atom in a compound containing two or more asymmetric carbon atoms is known as epimerization. So for example, let us see conversion of D-glucose into D-mannose. Glucose and mannose are epimers of each other. So let us change the configuration of one of the asymmetric carbon in D-glucose and convert it into D-mannose. So these are the steps which are involved in the conversion of D-glucose into D-mannose. The first one is aldose is oxidized with bromine water. So aldose means here D-glucose which is oxidized with bromine water. So bromine water is a mild oxidizing agent. So only the aldehyde group undergo oxidation and converted into corresponding carboxylic acid. So the aldehyde we have taken, that is the D-glucose. So on oxidation it becomes D-gluconic acid. Then this is heated with pyridine or quinoline. That gives equilibrium mixture of original acid and its isomer. So original acid is gluconic acid and its isomer is D-mannoic acid. At the alpha carbon, so this is the functional group, adjacent to the functional group second carbon becomes alpha carbon. So here configuration will be changed here on heating the compound in pyridine, or instead of pyridine quinoline can also be used. So equilibrium mixture of D-gluconic acid and D-mannoic acid are obtained on heating with pyridine. These isomers on heating, the aldonic acids on heating, they gives lactone ring. Gamma lactone. In the last conversion also we discussed it, gamma lactone. So adjacent to the functional group, this is alpha carbon, adjacent to the functional group alpha carbon, beta carbon, and third one is gamma carbon. So gamma carbon is involved in the ring formation, therefore they are called as gamma lactones. So both the acids are converted into gamma lactones by using a mole of water. So we want mannose. So this D-mannoic acid, the lactones which are crystalline compounds can be separated by fractional crystallization and one by one can be used for the reaction. So this gamma D mannonolactone on reduction. Reduction is with sodium amalgam in presence of dilute HCl. So they undergo reduction, the bond is broken, on both the side hydrogens are added. So again it becomes HCOH and this is CHO. So D-mannose is obtained. This is how the epimers are formed. So that is called epimerization. D-glucose is converted into D-mannose. Okay. So this is epimerization reaction. Next, see the interconversion of glucose and fructose. So first one, conversion of fructose into D-glucose and D-mannose, because both are isomers of each other. So when fructose is converted into aldose, means ketose is converted into aldose, two isomers are formed and they are glucose and mannose. So for that, here D-fructose is reduced again with the sodium amalgam in presence of dilute HCl. So when it is reduced, the C double bond O undergo reduction and it forms two isomers. So this is the configuration at the second carbon, the C double bond O. If the OH group is on right side, then it is D-sorbitol. If the OH group is on the left side, then it is D-mannitol. So while this formation, the functional group, that is carbonyl carbon, is converted into a new asymmetric carbon. So this second carbon is now a new asymmetric center, and depending upon the position of the functional groups, the position of OH group, there are two alcohols are possible. One is D-sorbitol, another one is D-mannitol. These alcohols on oxidation with concentrated HNO3, they are on heating with HNO3 undergo oxidation, and this alcohol group, see first carbon, that is alcohol group, this is converted into COH, that is oxidized into carboxylic acid. So we get here D-gluconic acid and D-manoic acid. Two acids. D-sorbitol on oxidation gives D-gluconic acid and D-mannitol on oxidation gives D-manoic acid. So again the same step, that is this acid should be converted into aldehyde. So for that, initially it is converted into a lactone ring, then reduction. So here on heating, the two acids are converted into corresponding lactones, gamma lactones, and these lactones, they are solid compounds, so separated by fractional crystallization. Then reduction is carried out. So on the reduction of these gamma lactones, so here reducing agent used is lithium aluminum hydride or sodium amalgam in presence of dilute HCl can be used, zinc and HCl can be used. So there are different reducing agents are present. So by using that reducing agents, the bond is broken, on both the side hydrogens are added. So one is D-gluconolactone gives D-glucose on reduction, mannonolactone gives mannose on reduction. So this is how the ketones are converted into aldehydes. D-fructose on reduction gives two alcohols, two isomeric alcohols, and that alcohols on oxidation converted into carboxylic acids, corresponding carboxylic acids. These carboxylic acids on heating gives lactones. The lactones are separated by fractional crystallization, then followed by reduction gives the aldehydes, corresponding aldehydes. So here fructose gives two aldehydes, one is glucose, another one is mannose. Now conversion of aldoses into ketoses. We have seen now the example of conversion of ketose into aldose, and now aldose into ketose. This is still simple than the conversion of ketose into aldose. So here the first step is the aldehydes, that is D-glucose, is treated with excess of phenylhydrazine. So already we studied this reaction, that is when the glucose, or that is aldoses or ketoses, carbohydrates, when treated with excess of a phenylhydrazine, they forms corresponding osazones. So here when glucose is treated with excess of a phenylhydrazine, it forms glucosazone. This glucosazone on hydrolysis, on acid hydrolysis, it gives glucosone. So here both the carbons, C double bond N is hydrolyzed. So this is hydrolyzed on both the sides. One side oxygen and another side 2 hydrogens are added. So it becomes HC double bond O and this is C double bond O. So glucosone is obtained. To get a fructose, this first carbon, which is aldehyde group, this should be converted into alcohol. So for that, reduction reaction is carried out. But there are different reducing agents, lithium aluminum hydride, zinc amalgam. They will reduce both the carbonyl groups, aldehyde group as well as ketonic group. But here, to convert glucosone into a fructose, the aldehyde group should be oxidized. So only for the oxidation of aldehyde group, the selective reducing agents are used. So here zinc in presence of glacial acetic acid is used. Here glacial acetic acid, in glacial acetic acid, zinc reduces aldehyde group in preference to the ketonic group. So that's why zinc in acetic acid is used as an reducing agent. Remaining other reducing agents, they will reduce both the carbonyl groups. So here the selective reducing agents are used. So in presence of acetic acid, zinc reduces aldehyde group than the ketonic group. So this aldehyde group is converted into CH2OH. Thus glucose is converted into D-fructose. So I hope you all understand these conversions and also the carbohydrate chapter. So here we will end the carbohydrate chapter. If you have any doubts, you can put a message to me either in a WhatsApp or you can mail it to me. So we can discuss about this doubts or some any interconversions or some terms which are difficult for you. Thank you, students.